Here in Chapter 11, we're going to focus on a couple of different topics, but we're only going to look at one particular section. And what we'll be doing in this section is looking at contingency tables and using the data that's compared in a contingency table to test for independence. And we'll be using the chi-squared distribution to perform the test. So let's define a contingency table. A contingency table is a table in which frequencies correspond to two variables. One variable is used to categorize rows, and a second variable is used to categorize columns. And when we're testing for independence, we're going to be looking for independence between the two variables that represent the rows and columns of our contingency table. So what does that mean? Well, remember that when we're talking about independence, we can go back to remember what independence means when we're talking about independent events. So let's recall that events A and B are independent if the probability of event A given B is the same as the probability of event A occurring regardless of whether event B occurs or not. Or the other way around, we could say that the probability of event B occurring given A occurred already is the same as the probability of event B occurs regardless of whether or not the event A occurred. Equivalently, we can define independence in terms of the multiplication rule. So for independent events, the probability that both event A and B occur is equal to the product of their probabilities. So this is going to be the case only when events A and B are independent. So the probability of event A and B both occurring is equal to the probability of A times the probability of B when A and B are independent. Okay, so that's really what we're testing here, is whether or not two events are independent. And these two events we're going to be organizing into a contingency table, and then we can look at the values, the frequencies that we're collecting in our contingency table to actually determine whether or not they're independent. And if they're not independent, well, we can maybe judge how close they are to being independent. Maybe here, before we move on to the next slide, it might be good to think of a simple example here. So consider the case where I'm taking a sample of people and I'm asking them two questions. Are you a Democrat? So the answer will either be yes or no. And are you under the age of 30? So their answer, again, will either be yes or no. So either their age is under 30 or over 30. So these would be two different variables. In this case, I would be looking at one variable here that's organized into the columns, whether or not they're a Democrat, and then organized into the rows, we got whether or not they're over the age of 30 or under the age of 30. Now let's say here I sample, let's say, a group of people, and I get the following values. So in this sample, we had 42 that were both Democrat and under the age of 30. We had 19 that were not Democrat and were under the age of 30. And then for the group that were Democrat and over the age of 30, we had 12. And for the group that were not Democrat and over the age of 30, we had 18. So a question here might be, okay, are these two variables independent? So that would be what we're trying to, the question that we would try and answer here now. So is the variable of being a Democrat independent of being under the age of 30? In other words, if I were to pick one of these people from the sample randomly, and I were to say what is the probability that they are a Democrat, given that their age is less than or equal to 30, if I were to pick somebody randomly, this probability here should be the same as the probability that they're a Democrat regardless of what their age is. If they are independent, that's what we would expect. But let's see, what would that be here? Suppose let's see, I choose somebody that's under the age of 30, so one of these people in the top row, and I want to know what's the probability that one of those people is a Democrat. So we see that 42 in the total of, let's see, 61 there. So I have 42 over 61 probability of choosing somebody that's a Democrat given that they're under the age of 30. On the other hand, suppose now I'm choosing one of these people at random regardless of what age they are. So not paying attention to what age they are, what would be the probability that I choose a Democrat? Well, here let's total up the number of Democrats altogether. We've got 42 under 30, 12 over 30, so that gives me 54. How many are not Democrat? Here I would have 19 and 18 gives me 37. And then altogether here the grand total would be 54 plus 37 is 91. So now looking at the totals here, I have 54 that are Democrat out of a total of 91. So I have a 54 over 91 probability that somebody in the whole group is a Democrat. So the question is, are these two probabilities equal? Well, looking at them as fractions, maybe it's hard to tell. But if I were to divide them and turn them into decimals here, the probability that somebody is Democrat given that they're under the age of 30 is about 6.88. And the probability that somebody is Democrat, 54 over 91, if I divide those, is about 0.59. So they're actually not equal. And so what that tells us is that these two events are actually not independent. So being a Democrat and being under the age of 30, in this case, seem to have a dependence on one another. And so now the question is, how strong is that dependence? And that's what we'll be trying to answer now with our test for independence. So let's look at the steps for performing our test for independence. And the first thing is going to be taking the values in our contingency table. So we'll have to mention that here, that the values in our contingency table that were given are going to be called the observed values. And we'll usually denote those values with the letter O. And then we'll compare those with what we would expect if those two values were, or if those two variables were independent. So we can look at each entry in our contingency table and compare that with what we would expect to see if those two variables are independent. And so the expected values that we get, so E here representing the expected value, would be what we would get to, in the entries of our contingency table if in fact those two variables are independent. And the way it's computed, we look at the row total and the column total and divide by the grand total. So we'll look at that in a moment, how that's done. But essentially what it does is it ensures that the probability of event A times event B is equal to the probability of both event A and event B. And then, of course, we know that that means that those two events would be independent. Okay, so that's the first thing, is to compare those expected values with our observed values. And then once we do that, then we can compute our test statistic, which you can see here relies on the observed values minus the expected values. So for each entry in our contingency table, we'll subtract observed minus expected values for each entry, and then the square of that divided by the expected value, and then we're going to sum up over all the entries in the table. And that'll give us our chi-squared value. And the way that the chi-squared distribution works, it's a little different than the distributions that we've seen so far, but it's going to be this right-tailed. Notice it has a skewed right graph, and so the right tail is going to be our p-value when we're computing the area to the right of our test statistic. So this will always be a right-tailed test. And notice that here, for the null hypothesis and alternative hypothesis, it's that the row and column variables are independent, is our null hypothesis. And the alternative is that they're not independent, that they're dependent. And of course, our level of significance will be alpha, like it's usually denoted. And so if our p-value, if we're doing the p-value method, goes below alpha, then we can reject the null hypothesis, in which case then we can reject the claim that the variables are independent, and we have evidence to support the claim that they are actually dependent. In other words, there is some association between those two variables. Now the chi-squared distribution is going to change depending on how many rows and how many columns we have in our table. And so what we have here is similar to when we did the t-distribution. You have degrees of freedom. And for different sample sizes, you have a different shaped curve. And the same thing happens here with the chi-squared distribution. The more degrees of freedom, we have a slightly different curve that tends to move a little bit further to the right every time we have a higher degree of freedom. But it'll always be this kind of skewed to the right graph. And luckily, though, we'll be able to use our calculator to help us compute the chi-squared value and also to compute the p-value for us. So we won't necessarily need to worry so much about the degrees of freedom, since that'll all be given in the table that we enter as our input. So now looking at how do we enter this into our calculator? Well, there's two things that we have to do. First thing is we're going to enter our table of observed values into a matrix. And once we do that, we can then input that matrix into our chi-squared test. So that will be the first part here, is to just enter all those values into a matrix. So we go to our matrix menu and then move over to edit, and then choose one of the matrices there that we want to enter the values into. So here they're just saying choose A, but you can choose any of those matrices that you have. And then we'll input the number of rows and columns into the size of the matrix, and then we'll enter all the observed values into each entry of that matrix. And then once we do that, then we can perform the chi-squared test by going to stat tests and then moving down the list to the chi-squared test towards the bottom. And there you'll enter, use the matrix that we entered the observed values in here. And that will be basically all we need for the chi-squared test. Now, what are the output for this going to be? So the output will be, well, it'll give you, like usual, the test statistic and the p-value. So it'll give you the test statistic, which of course is the chi-squared value, and it'll give you a p-value. And it'll also output the expected values are stored in another matrix. And you can indicate what matrix you want it to store those expected values in, so that if we need to, we can reference those expected values.